think that is an interesting question. And if everything is okay, OpenQA will be very important in openSUSE.
What is the documentation of installing this and those commands into creating repositories and so forth?
We have two versions of OpenQA. One is the one that this Berhan is using, and this version that is the one that we in openSUSE team we are using. This version is integrated with the Berhan integrates the certain parts of this version in his own branch. That means that in some moment in the official page of OpenQA will appear the current documentation. For now, we have a repository and a zipper update to install that. It's the only thing that we have. Yeah, there is some description, some documents inside the project, but it's not deeply documented. But yeah, we need to fix this in some point. And if everything is okay and Berhan publishes the new version, we will find the deployment information in the correct place that is his home page.
get this thing to display?
Power on.
It is powered. Yes, the LED is on. Yes. Oh, I like it. Technique to reduce locking potential by executing the code just in case, and you find out later on that you shouldn't have to revert the effect. Yes. For example, on my system it's TSC, means that I have a stable TSC. Yes. And if you dig long enough into this thing, then you will see that the TSC code does not use a spin lock. The same is true for the ACPI code. I have not yet checked the HPAD code, but it should be. An order is an order. No, I still have time.
Sprech.
There we have it.
Test, Test, Test. Sprechprobe. Der Sinn dieses Testes liegt in seiner schieren Existenz. Der Sinn dieses Testes liegt weiterhin in seiner schieren Existenz. Test, test, test. That was the sense of this test, is its mere existence. Test. Jo.
Hier, das müsste es sein.
Oh.
Ist das an? Das haben wir nämlich heute Morgen schon verwendet, deshalb. Müsste
Test, test, test.
merkwürdig. Heute Morgen hatten wir nämlich...
Mhm. Test, test, test. Geht das? Geht das? Na gut. Okay. So, what time is it? I'll give them another 2 minutes, unless anybody objects. Yeah. Was worth waiting, but I'll give people another minute. Okay. So, this is a talk about speculative execution, and I will begin with defining the program, then the method, and then the implementation, and then talk about the status. So, speculative execution aims to reduce locking. To understand why this would be desirable, I have to show you why locking is bad. Locking causes contention, and contention hurts scalability. To avoid that, locking has to be made as fine-grained as possible. That is, multiple CPUs must not wait on the same lock. To achieve that, we break down our locks to the smallest possible parts defined by which parts of a data structure must be changed atomically. That has consequences. Our data structures grow. Now you may tell me that you have a shitload of RAM. Then I tell you, you may have, but you do not have a shitload of cache, and your working set better fit into that cache, or you have a problem. In addition, usually you just can't take the fine-grained lock, but you need to lock your hash table, find out the element, lock that, release the lock of the hash table, execute your critical section, and so on. And we have 2 locks taken and 2 locks released. Quite a lot of computation. It gets worse. It's not just computation, it means writing. And it means necessarily writing out to main memory, because all CPUs must be able to see your lock being taken. And to add a bit of sadness, that is in principle, without lasting gain, because you release the lock, as you hopefully plan to do, it's back in the old state. Nothing gained. And, make it even worse, that writing has to be done atomically. On x86 and the 64-bit architecture, you take the lock prefix. That's expensive, about an order of magnitude. And we can make matters even worse. I like this, it's so nice and pessimistic. If you have lock contention, then you are by multiple CPUs in sequence, which means it cannot stay in cache. It will have to migrate from cache to cache as each CPU takes the lock. And that is quite expensive because it requires inter-CPU communication. So, anybody still convinced that locking isn't bad? No. We go to speculative execution. This is the first historical incident of speculative execution I was able to find. It was from the priest of the crusade against the Catholics. It sums up the method. You do something on a mass speculation, and if it turns out that you were wrong, you try to undo the effects. That is the basic principle here. It needs some kind of hardware support, which is being introduced in modern CPUs. The most obvious example is Haswell, upcoming CPU release from Intel, but we know AMD has made public that they will follow up. And the same principle, though in a set obviously, is supposed to be implemented in Power version 8. In this talk, I will talk about the Intel instruction set, just for the simple reason that that is the only kind we have. Intel itself is implementing 2 versions of speculative execution. The HLE and the really cool one called the RTM. HLE is backwards compatible. It works by one of the prefixes which on x86 translates to NOP, so you can run on older CPUs without change. It's just a bit larger. RTM is not backwards compatible. It has quite some new features, and they require use by the programmer. You can tell whether it is supported by the CPU ID instruction, as usually. Speculative execution works by telling you that a section of your code is critical, which other CPUs may not enter at the same time, which is the conventional view of this point. Under speculative execution, they may enter and they may do something. And at the end of the critical section, we find out whether this was harmful. In order to do that, you can see all cases in a critical section as atomic. That means they must either all succeed or none of them will succeed. This is done by the CPU not performing write operations. All writes are cached in special buffers and done after the end of the critical section. That has consequences. And what is done if the CPU finds that the execution was a bad idea depends on whether you use HLE or RTM. Under HLE, it just returns to the beginning of the critical section, which hopefully then contains your code for taking a log, and the execution is entered non-speculatively, which means that your log will be taken, and that's it. Okay, and the abort, if it should happen, happens fully under CPU control. Software learns nothing about the reason or whatever. Let me introduce you to the memory model here used. As I told you, this is not executed as far as other cores are concerned, but in the CPU, a cache line is, cached. There is no separate word for this. The cache lines have a status. It's either not used in the critical section, then it does not concern us, or it might be read, or it might be written. So, the CPU stores this state for everything it touches in the course of execution in the critical section, and at the end, it uses presumably the cache coherency protocol, but Intel hasn't told us that for sure, and compares its status of other CPUs. And now then looks, has anything I have read in the course of execution been written, then I cannot trust the consistency of my operations and must abort. The same is correct for having written stuff. And so we see that the logging is by hardware broken down into the most fine-grained form possible. Well, not possible, the most fine-grained form determinable in hardware. I'll come to that a bit later. There are obviously operations which you cannot do speculatively. If you're done in I.O., it's done. It can't be undone. So, there are operations which cannot be speculatively done. In, out, system calls, clearing the interrupt state, all of that isn't speculatively. Is specularizable a verb? Well, probably not. Would be made speculatively. Interrupts and page faults and task switches have the same effect. Also, the CPU store its writes. The CPU cache is limited, and if you run out of space, the CPU will also abort. There are three operations in RTM. In HLE, there is start this critical section and end it. It's a prefix. We have three operations in RTM. It's xBegin, which begins the critical section. Then it switches the CPU to speculative mode. And in addition to just beginning it, you specify if the speculation failed. Then the CPU will branch to speculative. That branching may happen at any time, whenever the CPU conflict, or at xend, which will trigger the full comparison and then either commit or roll back. Under RTM, in the market difference to HLE, you can do the abort in software. If in software you've detected that there is a condition which will not allow you to successfully finish the operation, you better fail soon. You only burn resources. And to make this nicer for the pro, you learn about the reason for the failure in the alternative. It's stored in the processor register, and if you use exabort, you can even send a short message to your. So now let's look at the algorithm which you perform to use RTM to remove locking. You could use it for other purposes. Right now we will look only at locking. The operations I'm using here are those defined for libc to use for the pthread library, but the algorithm itself is generic. You begin with starting with a critical section. This may fail if you try this on a CPU that doesn't do speculative execution. Then you check the log. This is necessary for two purposes. One, you may race with another CPU which has already and is now in its alternative code path, and then presumably it has taken the log. This cannot be done by comparing nodes, because the write to take the node has already happened, and in your perspective it would be too late. So the log to be taken, which can be seen by you've lost, you run in contention, you have to do the task switch and sleep. But even if you find the log to be free, this has a good purpose now. The log, or specifically its address, technically speaking, is in your set of cache lines you have read. If somebody else takes it, there will be and a clean abort will happen. Now, after that, you do what you wanted to do, and after it, you check the log again. For two purposes. Once, in that case you have written to the log, you need to free it, or you will deadlock, or somebody else has taken it while you were doing your critical stuff. So it's sad, you lose again, you have to give up and abort. In the alternative, that should be the more common case, hopefully. The log is free and you use xend. You can't do that unconditional xend, one node will cause a protection fault. Okay. This algorithm can be used in user space and in kernel space, and let us look how it is used in user space, which is done by the pthread library. Provides us with a large variety of logs, and we would try to use most of them by execution. Pthreads itself is these days a part of glibc and provides this to the user space. So the aim here is to modify only glibc and to speed up by reducing contention everything that uses the pthread standard. The use of speculative execution in glibc as far as the current patch set is concerned can be controlled by environmental variables. It uses speculative execution. It uses the xbegin and xend within glibc in the algorithm I had just demonstrated. And the alternative itself is also in glibc and consists at the beginning of the simple measure of actually taking the log. The end, that is the release of the log, is a bit more complicated. There are reasons for this. First of all, speculative execution only makes sense if contention can be avoided. If all your users use by writing and reading, it makes no sense. You do have contention. It's unavoidable. Secondly, your critical section is limited in size by the CPU, and it is limited in the kind of operation. You cannot speculatively do I/O, which is covered by aborting the procedure on syscalls. In the RTM code, you learn the reason of the failure, and you can do statistics. So, the glibc evaluates the statistics, and if there are too much execution, it doesn't try. You can also force that by annotating your log. You can do it in two ways. That is, you can force the attempt actually, for what it's worth. What are the effects of speculative execution? An abort of a speculative section actually causes a performance event on the Haswell CPU, which in principle can be read by the perf subsystem if you use kernel patches not currently upstream. Yeah. Speculative execution is every log in an RW log, whether you like it or not, because concurrent reads will succeed, while a write with the read will not. It furthermore gets you locking granularity at the cache line level. That is on the level of every cache line you have used. This is not necessarily the fine rate level you have, because it may be possible that you have touched a cache line which is not critical, but or turns out to become not critical in the critical section, but the CPU cannot possibly tell. It would need artificial intelligence to do that. For the programmer, this means that alignment has now become even more of an important thing. If you put two things in the same cache line, you will get false negatives. So, how can we do this in kernel space? It turns out we can, but the technology is immature. Let me go to the details. Let's have a short overview. The kernel has, again, a multiple of primitives. Spin locks, RW locks, mutexes, RW sums. All those are the bread and butter of kernel locking stuff. You just use them. There are a few old primitives like semaphores and exotic new ones, the sequence locks. Does the RTML lock still exist? Who knows? And CAS. For our purposes, we like to take as many locks as possible, but of course, a semaphore, it just doesn't fit any model. How would you do it? You have a defined number of entrants, and that can't be done speculatively. It just makes no sense. The exotics would in principle be possible, but they're too exotic. So, in kernel space, the same algorithm as I previously displayed will be used. So the alternative is simply taking the log, and at the end, there is some additional work. Again, in the kernel you have the same trade-off as in user space. It makes no sense to try something speculatively which you know to be extremely unlikely to succeed. You better wait and use your CPU cycles for something else. There is in the kernel the possibility that your CPU cannot do speculative execution, and we certainly don't want to publish a kernel flavor for speculative CPUs, which is at the CPUs. So we use for the UP when we use a spin lock, we modify the kernel code at boot time. Then the dynamic tuning, yes, this is done. Yes, it mustn't be done. We knock them out.
So, how can you dynamically alter this code?
You can't do it dynamically, but you can do it at boot time.
During boot time, you will decide that your CPU supports this,
And if it does, all is well. If it does not, you walk your list of recorded spin logs, replace the X begin and X ends and X aborts by NOP.
I was thinking about doing this earlier, but this is even more.
Let's discuss this later. There is, as in user space, the dynamic tuning, which is a bit problematic because it requires you to add counters to spin locks. You have to record the effect of failure or success somewhere. Then the patches which Intel has posted are very, very specific to their instruction set, so that they reject it in favor of a common model with pthread. We do have some problems. The feature is not fully understood. For example, how about memory ordering? Then we have to add counters. This is critical. Spin locks are very often used in embedded data structures. The current implementation is Haswell specific. Then we know that speculative execution cannot be nested, and spin locks are nested quite often in the kernel. You cannot switch off or enable interrupt in a speculative section. We will cause an abort, which is something we do in the kernel as well. And of course, we are dealing with our debugging equipment. It is built on the old-fashioned but sensible assumption that a lot is actually taken. And the point of speculative execution is not doing that. So debugging is short. There's a few more specialized uses of this. The KVM guys tell me that they would like to handle the page table misses in XABORT sections. Don't ask any questions to the specifics here. And then we know about a few further extensions planned to be provided by other vendors. I told you that the CPU cannot compute an optimal set of granularity because it does not know the semantics of memory accesses. There is, for example, the case you walk a list. You will have to touch a lot of next pointers and do something to once you found it. Typically increase the usage count. The naive CPU will have to abort whenever you touch one of those list members you walked. Can't be avoided. But what can be done is introducing an instruction for telling the CPUs that changes to such members can be disregarded. That way it worked efficiently. Now to the status. The the stuff is in the tool chain. All is well in that regard. There are
for glibc, and they look quite usable. There are patches for the kernel, but they need a major review. Okay? We are SUSE, we are great. You can't sue us for this, and please work for us. Questions, and please keep in mind that I'm not strictly speaking a glibc developer. I'm a kernel developer and usually do device drivers, not such stuff. But any questions? I'll try my best. It is not, depending on what you do. You can realize algorithms by speculative execution which are not easy or in fact possible to do in another manner. Then you need to touch the individual software. If you want to remove locks only, that is locks in the pthread code, then you are done with touching glibc. To use such features in glibc, you need support in the tool chain. For that limited purpose, you are indeed happy with only touching glibc, tool chain, and the kernel. No other questions? I used 2 minutes too much. Shit. Come on. That is a speculation. Intel just says we can. How? But I mean, they can do this during the normal course of operation because they have strict memory coherency. So they must be able to do it.
So when you any existing code example, how to use something like this on PSX on
PSX?
doesn't matter. I mean, do you have any existing code?
Yeah, that algorithm for eliminating a lock that has been published in patches for glibc by Intel, and more or less the same algorithm has been published in a set of patches for the kernel.
Should the numerous instructor to support? Or
No. I mean, there is academic research on transactional memory, what they call it. But technical examples current the lock elimination.
I know that for lock in theory itself, I can understand, but just in the I don't see code and then I don't know how to use it.
You shouldn't need to think about how to use it. It's just that your scalability is done for you in hardware. That's the point of the thing.
So there is no any explicit code I need to write.
You need to get your cache line.
You mean that I don't need to modify the source code?
You shouldn't need to. So nobody has told you how to switch this thing off.
So we don't need to check the code.
If you use a simple mutex,
What's the log?
in kernel space, this is a bit more interesting because we do memory mapped I/O. Not quite so simple.
If we just ignore
You can't I/O. That is not enough. In user space, you can be more because you have the system interactive system.
you cannot imagine that application, there is no modification on the application. It works.
You could do more to modify your application. That doesn't mean it's necessary.
I guess from the slide, I guess at least I should write some code to register how to abort it.
Sure. If you, in your library, at the same time, try the abort and something will not work.
I guess at least someone should register abort your code.
You can have speculative stuff is not necessary. This you can have only one abort handler at a time. And if Philip C uses it, then it uses it. You can't do it at the same time.
Okay. So but there must be something to register the abort code.
Yes, Philip C.
So if kernel uses this, kernel also has to register the abort code.
Yes. There will be a generic abort code for the type from. That just takes the log.
Awesome.
Simple case. The
Okay.
main question is, can we get away with trying speculative execution every time? Memory map I/O.
So the binary code should be modified. Just so we don't need to modify source code because we need to label, or maybe we don't need to modify both application and the label.
You have to make up your mind. Either you modify the application or the library.
I mean, if we modify the two chains, maybe we don't need to modify source code.
No, the two chain is just introducing some new parameters and stuff. Debugger support for that stuff. That's shitty. Because key tracing, of course, is a syscall, and then not quite finished.
Thank you very much. So you go back to Munich tomorrow? Forget. Something for you. Take it. I don't know what's that. Just a burner from the gas.
Oh, that kind of relax.
See that? Maybe there's some later outside in next year.
I need to go to the supermarket today to get some stuff for people.
Can you find supermarket? I'm not able to find any supermarket.
Apparently there is one in the direction of the new one, not the city.
Big.
I don't know.
I found very small, something like 7-Eleven.
I asked actually in the directions, you can ask for the game.
I see here to finish it.
Oh, I see.
I found some very small supermarket.
You need to finish the email, presumably to China now.
Just a moment ago, upstairs, I talked to just a board member from someone from here. We talked about answer, and he wants to make note for some important information. So I promised that we don't have to send an email. Yeah, maybe similar things.
You will not touch on 50
We want a 60. I just tell him